Hello and welcome back to my calculus guide videos. Just to let you know, I had a glass of juice before I started recording this video, so hopefully my voice sounds a little less dead than it did last time, though I can't really guarantee anything. One thing I forgot to mention in my last video, which was the second part of the fundamental theorem of calculus, was that one of those integrals that don't have the bounds, like this one, is what we call an indefinite integral, because we don't know from where we're defining it, and so that's the type of integral that you just have the antiderivative plus c, the constant of integration. So that's just something I forgot to mention, and hopefully, yeah, I guess now you know what the two types of integrals are called. You know, it's just always nice to have that little bit of vocab, in my opinion. Okay, so now, like I mentioned in the last video, I'm going to be talking about some more methods of integration, and in this part, I'm going to be talking about U-substitution, which, in my opinion, is pretty simple to understand, and actually is kind of fun for me. I don't know, it's a fun process to go through. So, use U-substitution for undoing chain rules of integrals. So, on my handout here, right, I just put a basic list of steps, and I guess I'll just write them down again and read them to you, and give you a couple of examples. If I can fix my view first. So first, you're going to replace the inside function of your the function you're integrating with u. U equals your inside function. So next, what you want to do is calculate the derivative of u. Find du dx. So next, you want to solve what dx would equal, so you can replace your dx with du. So dx equals blank. So then you will substitute, it will be something times du. So then you'll substitute your du into the into the integrand to find the substitute into the integrand. So substitute du. So this may sound kind of complicated right now, but if I show you a couple of examples, I'm almost certain that you'll understand what I'm talking about. So next, you're going to integrate the function, and when you substitute du, hopefully you'll be getting rid of all the x's in your function, so everything will be in terms of u. Your function will be defined by u, and instead of a dx, you'll have a du. There'll be no more x's in your equation. So if that does not happen, then it won't work. So next, you're going to replace your bounds in terms of u, if you're a definite integral. If you're an indefinite integral, you just stop there and add plus c. So if definite, reevaluate, find bounds in terms of u. So then you just evaluate using fundamental theorem of calculus part 2. So that was kind of a long process, but I might not have explained it that well when I was rambling. But now with an example, let's say find the integral of x plus 2 to the 5th dx. So our inside function is x plus 2. So we're going to make u equal x plus 2. And the derivative of u equals 1. Because this is 1, this is 0. So du equals dx. So what we can do now is just substitute du for dx. So we have the integral of u to the 5th times du. So now we can take the antiderivative of this and get u to the 6 over 6 plus c. And that's not actually, I forgot to mention this in my little step checklist. You have to substitute what u was originally back in. I should put that in my handout right now. So instead of u to the 6 over 6, you need to put back x plus 2 for u. So instead of this, you'll have x plus 2 to the 6 over 6 plus c. So yeah, I'll give you another example now. The integral of cosine of 7x plus 5 dx. So our inside function is 7x plus 5. So u equals 7x plus 5. Du dx equals 7. Du equals 7 dx. dx equals du over 7. So now I'll substitute that for dx. Cosine of 7x, cosine of u times du over 7. And now we can just take the integral, antiderivative of that, using the constant multiple rule. I don't know if it's actually called that, but that sort of rule, we can change that into 1 over 7 times cosine of u du. And like I showed you in the last video, the antiderivative of cosine is sine, so we're left with 1/7 sine of u plus c, and we substitute 7x plus 5 in for u. So this is our final answer. So yeah, now I'm going to show you an example with, before I do that, sorry, you'll notice that I turned this 7 into 1/7. Just to note, you can only substitute in for du if du is equal to dx, or if it differs only by a constant. If, say, my inside function was x squared, 7x squared, then the derivative of that would be 14x. And you can't substitute that in because doing so would put another x in an equation that's defined by u. So you can't do U-substitution in those types of situations. So now I'll be giving a definite integral example. So the integral from 0 to pi over 4 of tangent x secant squared of x dx. So if you are well aware of your trig derivatives, you'll know that derivative of tangent of x is equal to secant squared of x, which will allow us to eliminate the secant squared x term when we put in the derivative of u. So we're going to make tangent of x our inside a function. So u equals tangent x du dx equals secant squared of x. Du equals secant squared x dx. So du is just that. So now the integral from 0 to pi over 4, u of integral of pi over 4 and u of 0, is equal to u du. So the integral of the u du is just u squared over 2 evaluated at u of pi over 4 and u of 0. And since u is tangent of x, u of pi over 4 is 1, and u of 0, tangent of 0 is 0. That's just your basic unit circle, which I don't know if you noticed this, but you pretty much have to be pretty solid with your unit circle for this course. If you aren't, I recommend you just study a little bit. That's what I ended up doing, and yeah. So now we just do the fundamental theorem of calculus part 2. So 1 squared over 2, 1/2, minus 0 over 2, that's 0, equals 1/2. So yeah, U substitution is really simple. pretty easy for the most part, and kind of interesting and fun for me. So the hardest part, I'd say, is just identifying your inside function, but if you have a solid understanding of all your derivative rules and your antiderivative rules, you shouldn't have a problem, too much of a problem trying to identify the function. But like I mentioned earlier, substitution fails when you're finding the integral, when you're trying to substitute du in any differ by more than the constant. So that's where this next technique will come into play, and I'll see you on the next video.